I guess we can go ahead and get started. I'm Jared Longfox, one of the hosts and organizers of this AIAA Space Resources webinar series put on by the American Institute for Aeronautics and Astronautics Space Resources Technical Committee, specifically the subcommittee focusing on education and outreach headed by myself and Joe Kenrick from Lunar Outpost. I'm at the University of Central Florida, but the show isn't about me, so without further ado, welcome everybody, and I'd like to introduce you to John Culton from the University of Adelaide in Australia. Andy Thomas, Center for Space Resources, here to give an overview of some of the work they're doing down on the other side of the world, from me at least. I know we have attendees from all over, but so without further ado, John, if you're ready, go ahead and take it away. I'm here if you guys need anything, and feel free to punch questions in the Q&A as we go. We'll have a Q&A session at the end, and we'll take them in the order received. So, John, go ahead, and thank you for your talk.
Great. Thanks very much, Jared. Very much appreciate the invitation, and thanks for everybody taking time out of your busy afternoons to listen to me discuss some of the activities of the Andy Thomas Center for Space Resources. So let me just switch you over to the slides, and we'll get started. All right. Again, thanks for attending. We'll try and run through this presentation here. Keep it less than an hour, so there's time for questions if you have any. But what I'll be talking about today is what is the center, what's our particular philosophy as we look at this challenge of going back to space, and then, as NASA says, this time to stay. So how do we look at that challenge? What sorts of things are we researching, and how might we would love to work with any of you in the future if you see any possibility of collaboration, of mutually beneficial collaboration. So before I move to the next slide, I will just mention, like it says on the slide there, the Andy Thomas Center sits inside the School of Architecture and Civil Engineering at the University of Adelaide. So that the reason I highlight that is because, of course, that means that not only is the school full of civil and structural engineers, but also environmental engineers, water engineering, et cetera, and then every different form of architecture. So these kinds of people are used to building things, generally for use by human beings. And those things that they build are built by, of course, using human and increasingly robotic labor. So I just want you to get a sense for that, because that probably affects how we look at these sorts of challenges posed by, say, the NASA Artemis program, et cetera. And you'll see, we'll touch on some of that as we go through the presentation here. So what you should be seeing is a picture of a nominal sort of Australian lunar base. So you can see the yellow and green colorations for the astronauts and their equipment. That's of course, the Australian international sporting colors. But you can see a lot of things in this picture that we're trying to highlight. It does have a very definite civil engineering and architecture focus. So we're looking at building roads, building pressurized habitats, building unpressurized, rover barns, spaceport facilities, lighting, power, transportation of expendables, fluids, et cetera. But so all of those things, including a stockpile and parts depots and things like this, that we're used to seeing on a construction site on Earth. But as I said, we're interested in human things. You can see our mission, our mission statement at the top of the screen: enabling long-term human presence in deep space. So three big pieces of that would be long-term, humans, and deep space. So we are interested in what is happening with humans for long periods of time outside the protective environment of the Earth's magnetosphere. So in the full space weather environment. But that interest in humans and that interest in human activity in space extends beyond just supporting those activities with engineering and science. We're also interested in the legal, regulatory, policy, and international affairs aspects of this. So our team has been formed to incorporate that. And just as one aside, in this picture, if you look towards the horizon in the middle of the picture, you can see what looks like a star on the horizon just above that distant habitation facility. But if we zoom in on that, then we can see that actually that what looks like a star is actually the top of a tower. And what is that tower? That tower is an intelligence, surveillance, and reconnaissance tower put up by a neighboring nation on the South Pole of the moon, and that tower is just outside our Artemis Accord safety zone. So everything that's happening in our facility is being recorded and absorbed by that tower. And you can imagine situations such as this emerging when we get a multinational presence on the surface of the moon. So we have a law, policy, and regulatory group that is looking at these kinds of issues and is active internationally in solving those challenges as well. So moving on, of course, the big anchor customer for us in the West right now is the Artemis program. Despite being a Moon Agreement signatory, Australia is also an Artemis program partner, and they were in the first tranche of 8 countries that signed the Artemis Accords when at the same time that NASA and the UK and some others did. So they were very early into the Artemis Accords, and now I think we're up to 44 countries that have signed the Artemis Accords, the latest being Dominican Republic just a few weeks ago. So, of course, many of you are going to be familiar with NASA's path to the lunar surface. So you can see this is sort of early days with 1 mission accomplished. We're waiting on Artemis 2 and 3, and this particular graphic ends with 1 astronaut on the moon. And then the next one, using the moon as a proving ground for further destinations such as Mars. And you can see that the numbers of astronauts are increasing, the duration of the stays is increasing, and the aggregation of infrastructure is increasing as we consistently return to the same spot over and over again, and we build excess capacity with all of this equipment that we're bringing. How does that link into Australia? So I've mentioned, how Australia is linked to NASA, but this was a vision that the Australian Space Agency came out with in 2021. And this sort of envisions Australia becoming a global provider of what they call foundation services. So foundation services means that Australia would be expert at constructing, inspecting, and maintaining off-world infrastructure. And of course, they do have quite an expertise at that in dealing with constructing, inspecting, and maintaining assets in the outback of Australia. So they do have a particular expertise here, and this was a pretty bold move for them to aspire to become expert at what they call foundation services. Here in the civil engineering school, we would call that off-earth construction, and the two generally overlap. Now, importantly, we're not necessarily we're not a space mining center. We're a civil engineering center in those regards. But of course, the Venn diagram for mining on the moon and doing civil engineering activities, they overlap by a significant amount, potentially 70, 80%. Excavation, transportation of bulk materials, et cetera. But we are a civil engineering effort, and we work with the space mining groups. So a year after the Australian Space Agency came up with that foundation services concept, NASA's STMD released some of their long-range requirements documents. And of course, for civil engineers, this got us pretty excited. So we've been through these things with a fine-tooth comb, picked out lots of stuff that we really like. So resource excavation delivery to ISRU plants of thousands of tons per year. We're talking about robotics that can move thousands of kilometers per year, potentially, when especially, our fantastic robotics on Mars move something like on average 4 meters a day. Clearly the kind of industrial machinery that we're looking for on the moon to enable NASA's vision are going to have to be orders of magnitude more robust and more capable. So we can see on here, we're talking again, hundreds to thousands of tons of material moved and product delivered. So again, we're just highlighting, and we really love this line at the bottom of that red box. Excavation and site preparation are required for all construction activities. So our university, we're a global top 100 research university, but something that we excel at even within that group is site preparation activities, rolling dynamic compaction, things like that. So to see that NASA understands that you're not just going to be able to build things on an unprepared site on the surface of the moon is music to our ears. And then they get really interesting here. So site preparation, so that just means clearing boulders. And in the case of the moon, that would be clearing boulders, leveling the surface, and then compacting it, and then testing that compaction so that you can sign it over to a construction crew and they understand what surface they're actually building on. So site preparation, thousands of meters squared of prepared surface. That's fantastic. And then look at this really exciting stuff here in the lower red box. So we're talking about building berms that are 4 meters tall, then ultimately 7-meter tall freestanding berm. That is a massive engineering challenge that gets civil engineers pretty excited. Or even trenching, 1 meter deep and then 3-meter deep trenches. Yeah, awesome stuff. So looking at all of that, and of course, there's lots more pages of that I didn't show you, but thousands of tons per year of things moving, that's not really, this picture is not really representative or wouldn't require any of those kinds of activities. So we understand that this is a cartoon that would sort of show an early Artemis mission, but we can see there must be something else going on here because that pressurized lunar rover didn't come down in the lander that you see in the background. So potentially that came down via the human landing system, the lunar optimized starship, which is probably somewhere off screen at a distant landing pad, et cetera. And so this starts to, when we look at all of this in totality, it starts to invoke, we're probably going to need things like roads, landing pads, and there's a whole host of other civil engineering infrastructure required to support all of that. So really interesting. Fortunately, we do see some humans here. And as I said, our center is focused on humans because we think humans are going to play a really critical role going forward. So I'll, before I get into sort of the different kinds of research kit and laboratories we have, I'll just touch on something that for some people is a bit of a controversial topic. And I'll just say that we think that human exploration of the solar system and the build out and construction of all of this infrastructure is going to require humans. Humans are going to be involved in that activity, probably not relegated solely to a shirt sleeve environment, teleoperating a robot from a chair. We think that they're going to be much more involved in that if we actually go and do any of this stuff within the next 10 to 20, 25 years or so. So we have one thing I would point out is we have, all of my life, astronauts have been government employed, but we're at this really interesting tipping point where commercial astronauts are now starting to become a thing. And certainly the commercial astronaut industry would be best described as fledgling at the moment, but we think that is going to grow by leaps and bounds as all of this moves forward. And of course, a big event that happened earlier this week with the SpaceX Starship booster being caught by the launch tower. I mean, we're moving in that direction where commercial astronauts, we think, will start to play an increasingly large role. You can think of it as military pilots versus commercial pilots. They're both pilots, but they're specialized, and you have government specialized pilots. And sometimes they'll leave the military maybe with 4,000 hours of flight time, but their commercial counterparts have 20,000, 30,000, 50,000 hours of flight time. They've seen and done a lot more than the military folks across their career. And we think that's going to be the same thing that's going to happen with commercial astronauts. So earlier this year, we saw the Polaris Dawn mission. It took 4 SpaceX astronauts up for 5 days in space. There's 3 flights planned in that particular program, and that will culminate with those 4 astronauts flying on the first crewed flight of the Starship. So on that first slide, they achieved these first three major goals. So highest ever human Earth orbit. So these commercial astronauts achieved that record. First civilian spacewalk for two of them, and using the first civilian-derived extravehicular spacesuit. Something else that's interesting, I think, about the crew here. So Anna Menon on the far left of the screen, she was hired by SpaceX. She's been working for SpaceX longer than this, but she moved over to become an astronaut in 2021. Her husband, that same year in December, was selected by NASA to be an astronaut. So Anna has now flown. She spent 5 days in space, and she has two more missions ahead of her. And her NASA astronaut husband, to the best of my knowledge, Anil, has not yet been assigned a mission. So she's rapidly gaining spaceflight experience on the commercial side. One other mission I would point out, this also happens to be SpaceX, but we have Axiom flying multiple humans to space with their commercial astronauts. You've got Virgin Galactic and Blue Origin, et cetera, doing the same thing. But this another SpaceX mission for AM2. These commercial astronauts here, I would point out that the gentleman on the left of the picture, his name is Eric Phillips. He went to university in Adelaide. He's an Australian, lives in Australia, and he's on this mission, and he'll launch in late 2024. Compared to the Australian Space Agency, which now also has an active duty astronaut that just finished training, Catherine Bennell-Pegg. She's awesome. She's on the board of our center, but she has not been assigned a space mission at this point. But Eric Phillips, the commercial Australian astronaut, has and is expecting to fly here soon. So we think we're at this tipping point where commercial astronauts will start doing more, setting more records, achieving more space firsts than the government astronauts. And we'll see how that goes. Last slide on this particular topic. An interesting quote from SpaceX, building a base on the moon and a city on Mars will require millions of spacesuits. Why? Why would you need millions of spacesuits if all the astronauts are going to be in a shirt sleeve environment, just watching the robotics do everything? I think it's because everybody understands that humans are incredibly good at doing extremely complex engineering and extremely complex construction, and doing that in extremely challenging environments. And the closest analog is probably saturation diving here on Earth. And on any given day, there's about 1,000 saturation divers on the planet that are working to maintain undersea infrastructure, and that's everything from oil and gas sector to communications and port harbor facilities, et cetera. So there's a lot to be learned looking at this, and we could probably expect that humans are going to be intimately involved, doing some of the hard, as they say in Australia, the hard yards on the moon and on Mars, and building out these facilities. But discussing this fully and having a discussion with those who have a different view would basically be a conference in its own right. So unfortunately, you're listening to a presentation, so I'll move on, and maybe in the questions, if you want to challenge me on some of this, please feel free. So with all that as background, what does our team look like? Well, we've got our director of research is a chemical engineer, and he's got his own space chemical engineering lab and 15 PhD students and postdocs, et cetera. Melissa Deswart is one of the best space lawyers on the planet, and she's involved all over the world. And she's the director of our space law, policy, and governance group. Anima Wyatt is a psychologist, and she's our director of astronaut autonomy teaming. Well, how will astronauts work together with the robotics? So our view is that it's not going to be just robots, and it's not going to be just humans, and the two aren't fighting each other for preeminence there. It's astronauts and robotics working together, and there's some good papers out there. Crawford is the author of one that talk about the order of magnitude increases in capability and exploration that can be achieved when the two actually work together well. So Anna and her team are looking at that. We've got AI, machine vision, and lots of other folks, including an artist in residence that works with us, because if we're focusing on humans in space, that means everybody at the university has a role to play in this, every school, et cetera. So our School of Humanities, School of Education, they play a major role in the work that we do. But we're a long ways away from a lot of other folks working on these problems. So it's been important for us to have connections into, I would say, the Northern Hemisphere and all the activity going on there. So we do have a number of important adjunct professors that are attached to our center. Many of you will recognize Angel Abud Madrid, the director of the Center for Space Resources at Colorado School of Mines, Hurdy Miyamoto at University of Tokyo, one of the 7 planetary geologists who can name things on Mars. Charles Ilachi is an adjunct with us, and he was the 16-year director of Jet Propulsion Laboratory. Mark Saunter from Deep Space Industries, one of the Deep Space Industry co-founders, and Patty Neumann, who's a young PhD and company chief engineer working on really interesting engines for use in space. So our team spans all of that, and we're deeply connected in with a lot of other things happening in the wider world. So although we cover a lot of ground, we have particular expertise in foundation services or off-Earth construction, space agriculture. The University of Adelaide is leading now a Australian Research Council Center of Excellence called Plants for Space. And this is a $90+ million effort with 38+ partners, NASA, German Space Agency, and Australian Space Agency as key partners to figure out not only how we can grow food in space, but one of the major streams of that is, well, a tomato is really sort of a bioreactor, so we could potentially program these plants to grow the binders that we might need for 3D printing or manufacturing. The plants might be able to grow medicine when our medicine runs out. We've had payloads on the space station from the University of Adelaide showing the degradation to ibuprofen, both inside the station and outside the station. So we know on long duration missions, we're going to need to replenish those supplies. And this is one way that we might do that. But really, that sort of means that we're focused on humans, so we have a very large psychology aspect to what we do. So those are sort of the 3 areas where we believe we really have something to contribute. So I'll talk very briefly about some of our facilities and one of the events that we have here. And so we'll move on and talk about our facilities. So we do have a mission control room. We have partners that are on the back side of all of the computer equipment. There's a lot of things in the room you can't see here, but we have commercial partners from around the world that assist us in connecting to a number of in performing the things that are on the screen here in terms of driving robotics all across the world. And this is the mission control setup we'll be using here in the middle of June when our University of Adelaide team competes in the IEEE telepresence competition that will be run in the United States, where they'll be operating rovers in the U.S. On Peterson Hill. And that, of course, is headed by Rob Mueller, who also is from NASA Swamp Works. So that's our mission control. But then we have sort of the flagship lab on our central city campus is called the Xterra's Laboratory, and that's the Extraterrestrial Environment Simulation Lab. And we've got quite a bit of stuff in there. These pictures were taken pretty much right as the lab opened, so it does not look anything nearly as clean as these pictures show, because now, of course, we've got nitrogen baths and things as we're bringing the regolith thermal vacuum chambers down to temperature. There's quite a bit of equipment now has been added to the lab, and it looks nice and dirty. I'm sorry I wasn't able to get you the pictures of this looking sort of well used. But we have 2 rover testing pits. One of those is sand, and one of those is about 10 tons of Lunar Highlands regolith simulant. We've got 2 regolith thermal vacuum chambers, a test chamber that's 0.5 meter cube, and then a much, much larger one that you can see in the picture there. A simulant library, and then a processing zone where we're actually making construction components out of simulant in a number of different ways, and a 6 degree of freedom mode. Being used there, and that is a psychology, education, hearing, to understand stress.
John, you're kind of cutting out while the video's playing.
All right, we'll get off the video then. But that's a novel experiment that's really sort of the brainchild of the School of Psychology. Their set of expertise is human performance in extreme environments and also human stress reactions. So we've developed scenarios where the test subjects will be driving that rover in a virtual helmet that's watching for gaze and pulse and eye dilation and all that kind of thing as they're on top of the simulator, and they're working their way through that scenario. But again, that's School of Psychology, Humanities, Education, Civil Engineering, and Mechanical Engineering. And this sort of just shows the multidisciplinarity of projects when you're working in a space environment. So we've got the sand pit, as I mentioned, with blackout screens so we can challenge our robotic, the optics and sensors on our robotic systems. And I'm skipping through the videos because evidently that's my computer doesn't like sending the video and voice at the same time. So apologies for that. But we have the lab is incredibly busy, and those couple of videos showed some of the different things that we're doing. The one with the inflatable was just looking at is it possible, instead of burying, constructing a habitat and then bringing the regolith to bury it to provide radiation shielding, could you bury an uninflated version and inflate that underneath the regolith to minimize how much material would have to be brought in afterwards, as well as other novel forms of bio-inspired robotics. So the regolith pit, of course, allows us to sort of increase the realism with regard to degradation of the robotics using the LHS-1E lunar regolith or Highlands regolith simulant. Hopefully you got some of that video there, but one of those, there is a large bio-inspired robotics group at the university, and it turns out that the one robot called the Roobot actually had the pretty good tests when it was moving in a simulated 1/6 Earth G. But when we want to step up the realism, then we can move over to the regolith thermal vacuum chambers. We've got two of them. They're in a much more advanced condition than the pictures that you see here. So we're sort of optimizing these to be able to do construction activities at the lunar South Pole. We're not looking to simulate the temperatures inside a PSR. We are looking to simulate the temperatures at a place where you would likely aggregate infrastructure and build a facility. So not at the bottom of Shackleton Crater, but perhaps on the Shackleton connecting ridge, that sort of area. So again, those were just a few videos showing some of the early work in those vacuum chambers, mostly just getting them certified and figuring out how best to get down to the proper torr settings without destroying our turbopumps. So boiling out the volatiles and things like that. So regolith simulant library, we do have a fairly extensive one. We work very closely with the University of Central Florida and the Exolith Lab, and we have challenged Australian Customs by sending down multi-ton packages of dirt in the last couple of years, and more is on the way. Although it's not really showing up very well in the picture here, this is really one of the more important areas of the lab, is where we actually turn the simulant into things like bricks. So that's a major focus of the lab. The terrestrial civil engineers in our school work very closely with Australian civil engineering industry. And so we're tied very closely to, well, that's neat that you can make this thing. Can you make hundreds of thousands of that thing? And can you make them quickly and cheaply? And do they have engineering specs that are repeatable and dependable? So we want to make sure that if we're going to make a brick, we don't use some bespoke esoteric thing that requires 5 or 6 days to make a brick. We need to be making hundreds of bricks a day if we're planning on using them to pave a lunar road, for example. So we've investigated laser sintering. This is actually, there was a novel scan pattern here. Normally sintering results in this very thin crust breaking, but we were able to extend that indefinitely. So this could support a suited human with an appropriate safety factor, but probably not very robust. And we can't really make this much deeper. And there's other presentations that talk about why just increasing the power of the laser doesn't work for that. For a number of you understand what I'm talking about. So we're looking at casting as well with different materials. And I just stopped the video, so hopefully you can still hear me.
Yep.
But yeah, great. Thank you. So we, that one of those was a flexible robotic arm that was operating inside a liquid nitrogen bath. So we have folks looking at what can we do to protect, if we can get a flexible arm that can really reach around 180 degrees, et cetera, and that entire thing can be coated in a sleeve that prohibits lunar regolith from getting inside the mechanisms. That might be something that's very useful in a lunar setting. This rig, the big video on the screen that I stopped there, this is a rig. It's the only one of its kind, but this rig has a scaled simulation of compacting technology and an instrumented soil bed underneath it, so we can look down 30 scale meters into the ground. We've had a couple of our grad students spent a week in bunny suits, basically switching this thing out and replacing all of the terrestrial soil with lunar regolith simulant. And now we're able to run tests of scaled lunar robotic infrastructure, conducting site preparation activities while we actually we've instrumented the bed so we can tell what's going on at depth. So that was a video of part of that rig in operation. Of course, we do lots of outreach, so to student groups of all ages. And one of the facilities that we use for that is one that we just opened last year called the Xterra's Analog Facility. So this is out at our farming campus, which is just outside the main city of Adelaide. And we have currently 4,000, soon to be 8,000 square meters of space that we have now modeled as lunar or Martian terrain, complete with a robotics laboratory and workshop and mission control and all of those things that you can see here in the picture. There's a little bit better view of what the larger external facility looks like in our ribbon cutting last year. And this is the site where we run the Australian Rover Challenge. So we've run it 4 times. And last year we had about 300 students in attendance from several different nations around the world. And this year we have 29 teams who've signed up from 5 different countries, and we'll probably be running 2 pitches at the same time this year, or when this thing runs at the end of March in 2025. As you may have been able to see from the brief video that played, we have turned the Rover Challenge into a spectator sport. So we have bleachers and big screen TVs, we have constant color commentary, and we broadcast the entire event live on YouTube for all of the families, friends, and teammates at the competing universities around the world. But it's open to the public to watch as well. If anyone has any interest in sending a rover to our next challenge, please reach out and get in touch with us, and we'd like to talk with you about that. So interestingly, we were doing some testing for one of the Australian Trailblazer rover competitors, ELO2, which is led by EPE, a company in Australia with a long history in robotics, and also Lunar Outpost Oceania. And we were doing some testing for them, and out of that sprang the idea for what we're calling the Crater Facility. So this is the picture of one of the ELO2 prototypes, and we went out to our farming campus, and these sort of lunar simulated terrain, all the heritage of most of these facilities, whether it's Swamp Works or it's the site out at NASA Ames or our own site, they usually start off as sort of an ad hoc tent kind of thing. And so we borrowed one of the farmers' sheds and set this facility up. And these are the kinds of video and pictures we were able to get using a 9,000 watt solar illuminator and keeping it pretty dark inside where we were testing. So we did testing for both some industry partners with aims at getting to the moon, and also the Australian Institute of Machine Learning and some of their orbital and surface projects that they're working on. So we validated that there's a need for this kind of facility. So now we are formalizing it, and we're building our own shed. The farmer wanted his shed back, so we're going to build our own much larger facility. So this will be a 15-meter wide by 32-meter long barn with a much larger bed in it. So this is not an actual architectural, formal architectural drawing. This is one of our architecture students threw this together for this briefing. So this is not necessarily what it'll look like inside, but the goal is to have a very large pit in the middle that's reconfigurable, so all those side pieces come apart, and we can move the dirt around to make sure that we've got the desired sort of work face. So it'll be a really big building. Essentially, the ceilings are more than 27 feet above the pit, and that's so that you can hang lights at various levels, and you're not getting reflectance off the walls or other equipment in the building. And of course, we're taking steps to minimize that kind of reflectivity. But this is something where we could do full-scale mission rehearsals with life-size props, which we have quite a number of those on hand as well, different landers, processing plants, etc. So we can set those up here, and whether it's a human in a simulated astronaut suit or whatever, we can conduct quite a number of activities in this facility, which will open next May, it looks like. So with all that, I'll just finish up here. We are a member of quite a number of missions going either to lunar orbit or the lunar surface. We were members of the iSpace M1 and M2 mission. And I'll just highlight that there were 3 astronaut deployed lunar surface science packages selected for the Artemis 3 mission. So 3 of those science packages were selected, and we are partners in 2 of those. The Lunar Effects on Agricultural Flora, so that's our Plants for Space Center. And then the Andy Thomas Center is a partner in the Lunar Surface Dielectric Analyzer, which is measuring sort of construction or deriving some construction properties from the regolith after being set up by the astronauts. So last slide, I'll just say that little red star down there, that's where Adelaide is. So we're not just in Australia, we're in South Australia. We would encourage you to please come visit us, and you can think of it this way. If you're coming from North America, essentially on a calendar, you're training for a trip to the moon, because it takes about 3 calendar days to get to Australia. So when I travel back and forth between Alaska and South Australia, I start early on a Wednesday morning and arrive in Adelaide late on a Friday. So at least on the calendar, it seems like you went to the moon. But we would encourage you to come down. Please reach out to us if you see anything here that might be of interest in terms of collaboration, and we'd love to have you come visit sometime. So thanks very much for your time and attention.
Awesome. Great talk, John. A lot of cool stuff going on. We do actually have a question in the Q&A, so I'll jump right into that. Karis Cosmos asks, we at Lunar Cargo perceive as the simplest geotechnical activity we need to put in place is to collect the finest pulverized regolith for making a cushion hill needed for the landing of parcels by the Macedonis system, as regards the vertical component of motion. Any work in that direction, they would be happy to outsource to interested, capable parties.
Well, so that's really interesting. I think I understand what you're talking about. I'm not familiar with the Macedonis system or your particular work, but would love to talk with you more about that.
John, would you mind if I punched your email in the Q&A, or do you have it up on screen that you can throw up?
Yeah, if you want to type that in, feel free.
Sure, let me grab it. I don't know it offhand. Let me grab it from my email. Just a sec.
So it's just my name, john.culton at adelaide.edu.au.
Am I able to hold on? I'm finding that I'm not able to ask a question in the Q&A, but so I can punch it in the chat. There we go. I know how to work Zoom, everybody, I promise. So everyone, it's John.Colton at can you repeat that? Uh-huh.
Adelaide.edu.au.
Perfect.
And
There we go.
yep, that's exactly right.
Perfect. I can type today too. What a day. What a happy Friday.
Yeah.
Um Karis says thank you. Um so I did people feel free to punch yours in the chat. I'll ask a few questions to while you guys type. But one that I like to ask someone who runs and has access to as many facilities and different types of work going on. And this is a completely unfair question, but you personally, what's your favorite?
Oh, of our facilities?
Facilities, projects, what have you?
So that is a tough question, Jared. I would have to say that I really like the human aspect. I think that's going to allow us to go faster, do more, etc. So the projects that involve people, I find to be the most interesting. Even though I am an engineer and that's the bulk of our workforce, but of course, even engineers are humans. So, when we talk about the plans for space, so eating food, and you can talk to the astronauts about how much they love food. They would harvest a strawberry or a leaf, on the International Space Station and eat that. And they talk years later about what that feeling was like after being in space and for months on end eating things out of a tube. So the psychology, when we say we're a center focused on space resources, it's because space resources will allow us to do things that are healthy for humans in the long term, right? So you don't have to send astronauts up in an environment that had to fit inside a launch shroud. Instead, we can build something that is actually healthier for a human psychology than living inside a small round tube, right? And the same thing with growing plants and delivering different kinds of food that would be reminiscent of the things they used to use on Earth. So it's the human stuff. So the things I showed on the screen, that full motion simulator with the VR goggles and having the students or the test subjects, they're formally called, um, work through that problem set is very interesting. We also have an ISS mock-up. So, and the purpose of that is again a psychology experiment where we're looking at if we put test subjects in that ISS mock-up, and it's the same sort of visual clutter and audio clutter that you have on the station. It looks like you're on the station, but we give the test subjects a stress test, and a stress test is basically just a math test. So, what we're looking at is, okay, if we have them doing this stress test and they have an actual plant sitting next to them, a real plant, what happens to the test scores? We know that plants improve human performance and decrease stress levels. Well, what happens if you have a picture of a plant, but you have a scratch and sniff so you can actually smell the plant, but you see a picture, or maybe you just have a picture, or maybe it's a fake plant that's made out of plastic or something like this. Where's the good trade space there for? Do I bring along a real plant, but that's going to require resources and maintenance time? Or can I get away with the plastic plant that smells like a plant and that still helps me relax and things like this? So those would be my favorite.
Yeah, well said. And yeah, no, I agree. That interaction between human psychology, I mean, I'm obviously no psychologist. I study rocks for a living. But yeah, I agree that that's going to be one of the more interesting intersections. And I think when we have boots on the ground on the moon, humans dealing with the scale of the field geology there is going to be really interesting too. The field does wild stuff for psychology. So
Yeah,
anyway, a couple more have popped up in the Q&A. So Daniel Culp asks, there are many organizations slash agencies working on these problems like NASA, ESA, DARPA, LSIC, Moon Village Association, ESRIC, and etc.
yeah.
Do you have any ideas on how to more efficiently harness these collective efforts to make this a reality?
Yeah, so it's my first instinct is to say, well, that sounds like a really long list, right? But the list of problems is orders of magnitude longer. And so we had a student group that said, okay, that they were analyzing, we were doing a project on, okay, when would you pave or not pave a lunar road, right? What would be the factors involved in that? And there's a lot of factors there. And in their sort of set of objectives for sort of designing a program to investigate that, they bit off the entire world. They have to solve everything A to Z, and that was just because the unknowns involved in making that decision are so incredibly numerous. No one organization can do that, so it's going to require all these different organizations. So the most important aspect there, as you say, is going to be coordination. So for us, we try and attend all these things. It's difficult from Australia because everything tends to be at about 2 in the morning for us, especially if you're trying to attend an LSIC function, which of course is extremely valuable to be there with all the movers and shakers in this particular space at the ISRU group. Um, but we want to attend these things in person. We go to Space Resource Roundtable. We go to IAC. We try and get to as many of these things as we can. And then, as I said, we have adjuncts from around the world who help us stay connected to these things. Because, of course, what we don't want to do is unnecessarily duplicate expensive sorts of facilities. Now, there's some duplication is required. It's not that easy to travel with the robotic system to another country and do work there. There's a lot of impediments to that. So there's room even inside Australia for more regolith thermal vacuum chambers or dirty TVACs, more regolith pits, etc. But it's a huge, huge number of problems, and we definitely want to complement, not compete with other efforts out there, unless it's necessary just because of geography.
Makes sense. Cool. And thank you. Another one in the Q&A, Siva Sakamuri asks, you stated that the timeline to see progress on this project is 10 to 25 years from now. How realistic do you think this timeline is, and what do you think is the main obstructing factor? Good question.
Yeah, that's a really good question, and it's one that everybody would really like to know the answer to. What is the timeline, right? So are we, is this like Apollo, where when they were setting up the Outer Space Treaty, they said, hey, we'll figure out what to do with space resources when that becomes something that we can actually do. So they sort of kicked the can down the road regarding those sort of thorny questions, because the possibility of using space resources for anything meaningful was just too crazy and too far outside our technical capacity at that time. So are we in a similar spot today where we're saying, hey, here's all this Artemis base camp stuff and building roads and this and that, and it's not going to happen for 50 years? Or is it nearer than that? So that's a fantastic question. I tend to think it's nearer than that. And the reason for that is that not only do we have governments doing this kind of thing, but we have multiple well-financed commercial entities that seem bent on doing this with or without government. Now, you can challenge any one of those statements. Of course, SpaceX comes to mind, but they're also a government contractor, and they derive quite a bit of their income from that. But they're actively developing other income streams that would buffer against the ups and downs of political spending on space. So I'm biased towards sooner rather than later when we compare this with sort of what we were thinking was going to happen during Apollo. And that's where we have a little bit of a problem with regard to robotic systems doing all the work. I think there is appetite and there's a large potential that we might be up there needing to do some of these things before we have truly highly ultra resilient robotic systems that can do these things. So we don't even have those in our terrestrial mines, and the terrestrial mining environment is orders of magnitude easier than the surface of the moon. Great question, though. Sorry, I didn't give you a definitive answer.
There are no answers. It would be weird if you could give us an answer.
That's true. That's true.
Um, okay. People feel for that's the last one that was in the Q&A. Oh, never mind. Anonymous attendee asks, is it possible for you to pick just one? What would you say is the nearest attainable goal for you? In other words, what is the next big step you are looking forward to completing in order to continue moving forward?
Hmm. Okay, so on a personal note, that would be my PhD. So, but that's a high risk kind of thing, and I'm sure probably a lot of you in the audience already have that. I know that I know Jared is working on his as well. But with regard to the activities of the center, I think what we would what's going to be maybe one of the most important things, this relates a little bit to the previous question, is when does this kind of work, so in our case, we'll simplify it and we'll say sort of off-earth civil engineering. When does off-earth civil engineering become something that you can actually feed your kids doing, right? So right now, there's very few places that you can work and you can do that. So Jared's an example. I'm an example. Probably some of you in the audience here. There's some people at LSIC that attend the LSIC meetings where that's the case. But it's relative to any other sector, it's very small. So for me, it would be very, very it would be extremely it's a key unlocking event when we reach that point where we actually have enough industry involvement and industry can become self-sustaining doing these kinds of projects. And then that's where, say, from a university perspective, that's where we become self-sustaining as well. Right now we're a cost center. We're not actually, the university has to have a strategic vision that this is an area that's going to be important for us in the future. And so we're developing this capability. What would be very nice is if commercial companies can also get to that same stage.
Agreed and well put. And yeah, as a university researcher as well, our group at UCF is the same thing. The university really has to have an aligned vision that this is going to be important. So
yeah,
I fully agree on the aligning of interests and priorities are really going to move a lot of this stuff forward in both academia, government, and industry.
absolutely.
There's not another one in the Q&A right now, so I'm going to sneak one in. There's fundamental differences between the geotechnical properties of lunar regolith and the soils here we deal with on Earth.
Mm-hmm.
What do you think is the best way to learn about and reconcile some of these differences so we actually can safely and efficiently develop infrastructure and explore on the moon, Mars, etc.?
Yeah, and that's, of course, you're involved in this day to day, so and you would probably be a better expert to answer that question than me. But I'm going to take the cheap way out, and I'm going to say, well, what do we need, Jared? We need Exolith Lab, and we need the Xterra's Lab on the moon, right?
Yes.
That should probably be a first order sort of thing that once we actually do set up shop up there, we have a piece of that terrain that we use for experimentation. So one of the things that I think you can look at a lot of different companies for this, but SpaceX is probably the one that is seen or the most visible. They're building all this incredible stuff on a beach in Texas, and Lab Padre and Boca Chica Gal and everybody else have cameras and fly drones around that site 24/7, so they're able to see what's going on there. So what they're doing is so interesting because they're able to rapidly iterate. So they can test and have an unintentional destruction or an intentional destruction, innovate, redesign, rebuild, and do it faster than government permitting will even allow, oftentimes, right? So what we need is our facilities on the moon so we can actually incorporate all of those important environmental factors in one testing area. And you get a lot of that for free if you do it up there, if you don't talk about transportation costs, right? So but vacuum is expensive, and radiation in a vacuum in a terrestrial lab is expensive, and these kinds of things. So for me, that'll be the most important thing, is that we're going to get up there, we'll have a lab, we'll have a facility on the moon, and we'll be able to rapidly iterate, and we'll come up with generation 10 of this equipment within the first year of testing up there.
Well put. Sounds like we need some budget to fly some stuff to the moon and start setting up, huh?
Absolutely.
Cool. All right. There are two more in the chat. We do have a couple of minutes, so I'll take these and then we'll end. Siva Sakamori asks, with this increase in astronautical investments and interest, do you think that the aeronautical industry would be in decline, or any other industry could be negatively impacted?
Yeah, I don't know. I think obviously on the space side, all of this increasing interest and increasing sort of reality that this is getting closer and closer. I think this bodes well for the space workforce. And then I think there's an inherent desire for people to become more mobile and continue traveling. So I see that the aerospace industry should be probably just fine for the foreseeable future, I would think.
Cool. And last one before we wrap up, Daniel Culp says, I saw Bandai Namco on your slides, a gaming development company, and you are working on turning robotic competitions into a spectator sport. Is there a grand strategy or way that we as students, researchers, and industry can help motivate the public through this entertainment factor? It might, in comments, that it might be a good PhD or paper topic if one doesn't already exist.
Yeah. Yeah,
Agreed.
and again, another excellent question, Daniel. So people have been trying to understand how to involve the general public. So I would imagine that of the 11 folks that are still online here, probably most of you have a STEM background. So you're already on side. You're taking some of your Friday when you could be doing a myriad of other things. And you're sitting in this, having this discussion. So you're already on the team. You're a card carrying member. How do we reach the rest of the world? And they're interested in this too, but this has historically been kind of a STEM only subject. So yeah, the Rover Challenge is a spectator sport. So we bring people in, we have constant commentary explaining what's going on and why it's tough and what the background of all the different tasks and things, the objectives that have been set. And like we do work with an Australian based gaming company to work to produce some of these things, for both for outreach in local elementary and high schools across South Australia and Australia, but we have a broader vision as well. And so, good eye, you saw the Bandai Namco name. So they're a partner in the iSpace missions with us. And so I don't know what their particular angle is on the M1 and M2 mission, but that shows that I think we're trying to get outreach. Multiple countries and multiple groups are trying to extend their outreach from talking to groups like AIAA, but also getting things out to students and kids and getting this in front of them at a younger age.
Well put. And I'm going to add a shameless plug for this webinar series to that. If this is an education and outreach oriented webinar series, audience members, and of course, John, if you guys know anyone in the public, kids, adults, no age limit, please, and they're interested in this sort of field, please refer them to these live events or the YouTube channel for the AIAA Space Resources Technical Committee. We're here to help and provide resources for anyone who's interested in this to learn more. So shameless plug on our public engagement. But with that, we are out of time. And John, I'd like to thank you so much for coming and sharing your group's work and all your thoughts and insights on the many great questions that people asked. So with that, I think we can wrap up, and everybody stay tuned for next month's webinar announcement at the beginning of November. So
Thanks
With
very
that,
much, Jared. It was a real honor and pleasure. Appreciate it.
of course, thank you again, John. And thank you, everybody, for attending and for your continued interest in this series. Help spread the word. Talk to everyone later. Bye.
See you.